All right, so I owe you a statement from the morning. So let me write down what it is that we were trying to do. So I'll sort of write it a little bit differently, this sort of linear algebraic fact. So instead of taking a n cross n symmetric matrix, I'll take an n cross n complex matrix. And what I'm interested in this integral. In the morning, we were looking at A transpose A. Now, instead of looking at A transpose A, I can also write it like this. This is essentially the same thing. And the claim is, so we want to find conditions so that I have all of this equal to 1. And what I said in the morning, I think I'll use a different pen. I only imposed this condition that the real part of A is positive definite. And of course, this is already a problem. If the determinant of A vanishes, this is not going to happen. So let me just explain. So you can, I'll sort of describe the additional condition one needs over here to get this equality and just the idea behind that. So if I write A as, let's say, the real part of A plus, so C is real part of A, D is imaginary part of A. And the way we are going to think about this, we are actually going to think of this as we want to think of this as a holomorphic function in A, right? So A has, so I think of this as an element in C n square. And as long as this integral is well defined, so if I have integrability over here, then I can just view this as a holomorphic function in A. So what that allows me to do is it allows me to check this identity on some portion and then maybe use the identity principle to push this forward. So the region where this is all going to be okay, so this is okay if the imaginary part of A is 0, then you can just do a change of variables using V equal to AU. So A is real now. You have, so this is non-zero, and so this holds if imaginary of part of A is equal to 0. So if I look at this axis over here, I have some cone where I have that this identity holds. And so I just need to describe to you some open set which kind of contains this cone over here, so that this left-hand side is holomorphic in A, and so then by the identity principle, this identity will have to hold in this entire open neighborhood. And so this really just comes from the fact that you want to make sure that you have, this is integrable over here, so you just need to study this. And so if you look at e to the minus, so I have c plus I dx, c plus I dx, and so it's the real part that really matters over here. So you get cx, then you have plus dx. Okay, and so if we have this additional condition, so I'll just impose this additional condition that if I look at real part of A transpose, so this is an additional condition, real part of A, then this dominates imaginary part of A transpose imaginary part. Okay, so once I impose this additional condition, so now this is some sort of right, so now I'm looking at this identity in this open region, and here the left-hand side is well defined. It's holomorphic in A. On this totally real slice, which is imaginary part A equal to 0, this identity holds. So there's a version of the identity principle which forces this identity to hold in this region. And the setting that we were in already at the origin, we were actually looking at a neighborhood of the point A equal to I. And so there we were guaranteed a small neighborhood where this identity holds, and that's how we would have chosen our delta naught. Okay, so this is the correct statement. So if you want to go back and think about this, this is the claim that I'm making. Over here, this is the correct statement. This is the additional condition. Any questions about this? Okay, so what I want to do, I'm just going to do sort of a bunch of miscellaneous things in the last lecture. I want to tie everything together, and so far we have been approaching these convexity problems through approximation, but I want to look at it a little bit differently. So I'll start with the definition, which many of you have already seen, or if not, it's sort of very hard to talk about complex analysis without encountering these. These are some sort of analogs of convex functions. I want to define what a plurisubharmonic function is. So let U be an open set and phi be a real valued, but I allow it to take values, I allow it to take the value minus infinity, be an upper semi-continuous function on phi such that phi is not identically minus infinity on any connected component of U. Okay? And this over here just means, if you haven't seen this before, this just means that if I look at, if I pull back these sets, these are open. Open for all C in R. Okay? All right. So it's some condition, and really we don't need this definition in this generality, but I'm still stating it in its complete form. And of course, I'm also going to say something here. So on any connected component, we say that U is plurisubharmonic, or PSH short, if for every complex line L, if I look at the restriction of phi to L intersect U, so that gives me some open set in L, which could be empty. So if it's non-empty, I consider this open set in U. L is a line, so you think of it as the complex plane, and I want that this function is now subharmonic. So I'm sort of assuming that you have, sorry, what have I done?
No, phi has to be not minus.
Oh, yes, of course. Thank you, yeah. And you could try to work with that, but you won't go very far. Right, so I'm sort of assuming you know what this means, but it's fine because I'm going to say something which will help you understand this a little bit better. But what we are saying is that along every complex line, I want subharmonicity, and that's what I'm going to call a plurisubharmonic function. And this is an additional thing I have to say, because maybe, I mean, it depends on the convention, but I don't want to allow for something like this over here, okay? And of course, with a definition like this, I mean, it's a little bit about testability. So let me, in addition to this, say that if phi is, so if phi is C2 smooth, then we have an operator that can test this for us. Then this is equivalent to saying that, so you've already seen the second order operators. I'm going to write it in two different ways. So I look at these mixed second order derivatives. This is your Levy. Once again, we are looking at the Levy form in the third mini course. And this when applied to complex vectors. So here C is in Cn, and it has coordinates C1 to Cn. This is positive semi-definite for all P in U and C in Cn. okay? And this is the same thing, I mean, said in the language of forms, this is the same thing as saying that if I look at I d bar phi at P, then this is a non-negative 1-1 form for all P, not a nice color, for all P in U. Just a slight thing that usually when people talk in this language, somehow they use positive for non-negative, but I'll just say non-negative just to be absolutely clear over here. And then what is really going to matter for the rest of this discussion is strict plurisubharmonicity. So if I want this to be strict, so further we say that phi is strictly PSH or SPSH at P if, so let me write this again, ZK bar, and here I'm really taking over in all directions. This is strictly greater than 0 for all non-zero, of course, non-zero vectors. And so this will be an important object from the point of view of the discussion that we are going to have today, but let me maybe just give a few examples and give a few properties. So first of all, this is a local concept, so you can really check plurisubharmonicity locally, and also this condition that we have upper semi-continuity over here, this tells us that PSH functions are bounded above on compact sets. Okay. In fact, any PSH function is in L1 lock, and what we have written over here, this differential condition, so I don't want to introduce a lot of language, but this condition that we have written over here, this can be understood in some weak sense, and so we can understand, because of this integrability, we can understand, so let's say, let me write it this way, so phi is PSH implies phi is L1 lock, and then we can understand this in some weak sense. So this is a non-negative 1-1 current, and I'll not say more, I don't want to go into this, but if you've seen this language, then you might find this familiar. So in particular in dimension 1, I mean, if you don't remember what subharmonic is, subharmonic in dimension 1, this is just equivalent to saying that the standard Laplacian of U is greater than or equal to 0 if you have smoothness, and otherwise if you don't, then in the sense of distributions you're getting a non-negative Borel measure. Okay, so that's the same thing as subharmonicity. And sort of the key examples over here, and because I'm not going to prove anything, these are sort of all ingredients of the various statements that, if you want to go back and think about them, this might help you. So the key example, I mean, what does this have to do with complex analysis? So let's take something which is holomorphic in U, and let's assume that it's not identically 0 on any connected component of U. Then log absolute value of phi. Remember, we are allowing minus infinity. In fact, those are the interesting sets. Those are the interesting places from the point of view of PSH functions. So this is PSH, and absolute value of f to the alpha is also PSH for positive alpha. Okay, so these are some good class of examples to keep in mind. Okay, so before we kind of go back to convexity, let me sort of point out something over here. So given a C infinity SPSH function phi on Cn. Let's say we have a nice global strictly plurisubharmonic function C infinity, which is C infinity smooth, then this 1-1 form dd bar phi, so this actually becomes a real 2 form. So they are, it's very nice because what it gives you, let me call this omega. So it gives you a symplectic form on Cn, which maybe it's worth reminding you what that is. So what is a symplectic form on Cn? You want this to be a closed 2 form omega, closed non-degenerate 2 form omega, and this, I mean, once you have a structure like this, this is sort of related to all the contact geometry that we were talking about in the other course, and maybe some of that will appear today. But so we have this symplectic form. Non-degeneracy just really means that, you know, if you have omega xy equal to 0 for all y in Cn, so this is acting locally on each tangent space, but here each tangent space is Cn, then that implies that x must be the 0 vector. Okay? But in fact, this is also a Kähler form, which is a positive, strictly positive, closed 1-1 form. So it's more than just a symplectic form. Okay, so we have this structure which is coming from this global smooth SPSH function, and we are somehow going to interpret, you know, these various convexity notions that we have seen using something like this over here. And so I'll come back to this, but let me come back to convexity and tell you why we are thinking about plurisubharmonic functions. So everything, I mean, these are all results that need proof, but these are all various facts that I'm going to state. So the one thing you can do, and this is sort of the connection to polynomial convexity, is that given a compact K in Cn, so I said that this is some sort of analog of convex functions, and that should be clear from a definition of this kind over here. So maybe I can construct a hull using this category of functions over here. So I can construct the PSH hull, and what I can do is I can take all these points where if I compute any PSH function, and I'm taking global PSH functions, then this is at most the supremum of this function on K. So let's say W in K, and remember we have PSH functions are bounded above on compact sets, so I take phi of W, and this is for all phi that are plurisubharmonic on Cn. So this seems like a completely different object, and there is no question. Sorry? No, these are real valued functions. So PSH functions are real valued functions. Okay, so I really am taking phi. Yeah, I've erased the definition, but these are real valued functions. Okay, yeah, right. So this is sort of an important fact that in fact the PSH hull is the polynomial hull. Okay, and this sort of brings some flexibility to these objects because, you know, it's much easier to work with PSH functions. So that is the connection to polynomial convexity. But I also kind of want to bring in this condition of being totally real, because we are trying, I mean, we sort of spoke about the Mergelyan approximation property, and we said that, okay, if we have a totally real manifold, we have AK is okay, and then if in addition to that we impose either rational or polynomial convexity, then we also have really good approximation. So we really want to understand that setting. But this, the way one gets this is another fact. So I'm just going to write all of these down. K is polynomially convex if and only if, so here's a characterization of polynomial convexity purely in terms of PSH functions. if and only if there exists a C infinity smooth, so I'm going to start using this notation, intersect, so it's a plurisubharmonic function, so there exists a phi which is both smooth and plurisubharmonic such that phi is non-negative on Cn, phi is strictly plurisubharmonic off of the set, and K is in fact the 0 set of this PSH function. So I can actually say more over here. I can also make sure that phi behaves like, so basically a good example over here to keep in mind is phi of z equal to norm z square. And so what I can do is I can also ensure that phi eventually looks like some multiple of this over here. Okay, so I'll not say that over here right now, but this is a way to characterize polynomial convexity using so the big thing over here, the main thing to keep in mind is I cannot always ensure strict plurisubharmonicity on the points in the set K. Okay, but I do have strict plurisubharmonicity off of K over here. Yes.
Just a stupid question. Why do you don't want to have phi is equal to minus infinity? Because it doesn't work if you include in the definition phi has to be different from minus infinity.
Right, but here it's no issue because here I'm anyway asking this to be non-zero. Yeah.
You could have as a definition also.
I could. I suppose here also it's fine. Yeah, I guess it's fine. Right now it's fine, but I think it's just sometimes useful to avoid it. Yeah. Sorry?
Suppose that phi is N1 log.
Yeah, okay, yeah. So for this, I guess this interpretation, which we are not using because we are working with smooth PSH function, so we are fine. Yeah, thanks. Yeah, yes.
Yeah, I mean, it's a bit weird that you're obliged to allow phi to take on the value minus infinity. Is that right?
Yeah, it's a bit, I mean, as you said, you will not have this, and then every time you'll have to throw it out, you'll be like, except for that one, and so you just throw it out in the beginning. Yeah.
Also, it's very cool that the right-hand side is independent of choice of coordinates, isn't it? Whereas the left-hand side.
This.
Well, I mean, polynomial holds.
Yes. So that's the big advantage that you need polynomials to define polynomial hulls. Although we did see, I mean, what is really, I'm a little bit cheating over here because this is really the O of Cn hull. I mean, we've done this umpteen number of times where we actually do approximation by entire functions, not by polynomials. And so as long as you have holomorphic functions, you can do this. But yes, at least if you just go by definition, it seems like this is much more flexible than polynomial hulls. Yeah. And the same thing with rational hulls. I mean, people do define meromorphic hulls in other settings if you want to sort of do this in complex manifolds or something like that. Okay, so I don't know, did I start at 3? Did I start at 3? Okay. So this, so we have this K, these polynomially convex sets as 0 sets of non-negative smooth PSH functions. I mean, being able to make it SPSH outside is an additional nice factor. But now, if we take a totally real manifold, and I'll just work with smooth submanifolds. So this will indicate a little bit why we are getting this nice approximation property for totally real submanifolds. So let M in Cn be a smooth. So when I say smooth, I really mean C infinity smooth. I can do with less than this. Be a C infinity smooth TR submanifold, compact submanifold. Then there exists some neighborhood U of M and an SPSH function in U such that phi is non-negative and M is really the 0 set of phi over here. Okay, so we have some totally real manifold, and what we are saying over here is that you are able to, in fact, okay, let's say that. So you're able to find some neighborhood around this, and you're able to find a very nice an SPSH function so that its zero set is exactly M over here, it's non-negative. And what's preventing this guy from becoming polynomially convex is the fact that this is not global. So if this guy was defined globally over here, we want to view, I mean, we can view polynomially convex sets as zero sets of PSH functions. We seem to almost have that over here, but the problem is that this function is not global. So what is preventing us from making capital M polynomially convex is the fact that, can you make this guy global over here? In fact, here you can take a distance square. So f of z equal to square distance from M, for instance. So now if you do have both these conditions, so this statement and this statement, if you do have both these conditions, you have totally real and polynomial convexity, that's very good approximation. So if M is TR and polynomially convex, then there exists a phi. In fact, I can write this as an if and only if statement. So let's say M is smooth and TR in Cn, M is polynomially convex if and only if there exists a smooth, strictly PSH phi non-negative such that M is exactly the zero set of phi over here. And remember, now that we have this SPSH function, we have a corresponding Kähler form on Cn. Okay? And what is the relevance of that? So, I mean, here it's the zero set of the potential, but it's kind of nice when we see this from the point of view of rational convexity. So this is a theorem by Duval and Sibony. By the way, I've already mentioned this, but if capital M is an n-dimensional real closed submanifold, then it cannot be polynomially convex. Okay? But here I'm allowing for lower dimension, so that's fine. Okay. So M is like this. So again, M is C infinity smooth, totally real. I mean, of course, if I reduce the smoothness over here, that does not affect this result. This result, the smoothness has nothing to do with the regularity of the set, but it does affect this. So near the set, we would not be able to get C infinity, but that's coming from this piece. Okay. So M is rationally convex if and only if, and so I will take this J map, which is the inclusion of M in Cn, if and only if there exists a smooth, so basically if there exists a Kähler form, so smooth SPSH function such that if I look at I dd bar phi and I pull it back to M, so let's call this Jm, that vanishes. And in the language of symplectic geometry, that means that M is a Lagrangian submanifold of this symplectic manifold. Okay, so in sort of the totally real realm, if you want rational convexity of your manifold, then you have to be able to realize it as a Lagrangian submanifold. So let me maybe say this, maybe there was a red pen. So definition, actually I'm sort of, let's be careful here. So I have not, the dimension is less than or equal to n. So let M omega be a symplectic manifold a submanifold capital N in M is said to be isotropic. So let me give an inclusion map said to be isotropic with respect to this structure if when you pull back this form on N, then this vanishes. And if, so a symplectic manifold is always 2n real dimension. So if the real dimension of N is half of this, then we say, right, that N is a Lagrangian submanifold. Of, sorry, M omega.
N is a real one.
Yeah, N is a natural number. Yeah, 2n real manifold. 2n dimensional real manifold. Okay. So how is that, I mean, what does that really give us? So the paper in which they have this, I mean, I sort of restricted my attention to totally real submanifolds. Like my compacts have been totally real submanifolds. But they have a much more general discussion where they characterize rational and polynomial convexity in terms of currents. And then they also have results for closures of domains. So I just want to talk about a few of these because this sort of is a more modern approach to convexity where you're sort of like the way we've been discussing it so far, we've been looking at specific sets. So I give you a set and I say, okay, is it rationally convex? Is it polynomially convex or not? But sort of now what people like to study is whether something has the topology of a rationally convex set or a polynomially convex set. I mean, okay, fine, maybe the given set is not rationally or polynomially convex, but can I maybe, you know, move it around, deform it a little bit, and then like, does it have the correct topology? I mean, it's not a purely topological property, but there are some topological constraints, and so these kind of results help us say a little, helps us eliminate certain types of sets. They just cannot have the right topology. So let me mention one more theorem over here before we sort of discuss those kind of, or maybe as a consequence of this over here, right? So there is, there's a very strong, I mean, being a Lagrangian submanifold imposes a very strong condition on the underlying topology. So you might say, okay, but it depends on this form over here. That's true. But the way this construction goes, you can actually make sure that this form, like if you're in Cn, so I'm talking about the Duval-Sibony result. If you're in Cn, you can make sure that outside a large ball, your form is just the standard form or like some multiple of the standard form. In that case, you do have a symplectomorphism, so you can essentially think about Lagrangian submanifolds with respect to the standard symplectic form, which is coming from the norm z square function. So for example, so corollary, the only surfaces, the only closed surfaces that can embed as TR and rationally convex submanifolds of C2, for example, are. And so we actually, I mean, for surfaces, there's a full description of what admits Lagrangian embeddings and what does not. So you have the torus, and we've already seen this embedding, and you're allowed certain non-orientable surfaces, and these are direct sums of RP2, and there's a constraint. So the number of these can be 2k plus 4, and k has to be greater than or equal to 1. So RP2 connects some RP2, the Klein bottle, that does not, I mean, this was sort of open for some time, but that actually does not admit a Lagrangian embedding into C2. So these are the only ones where you have both totally real and rational convexity, if you only care about n-dimensional submanifolds of Cn. And this is sort of an attempt to maybe just talk about a few open problems as well, even though I know that the session is later. So I'm stating a result of Shafikov and Sukhov. So here we are asking for very nice rationally convex embeddings. We are asking for something that's both totally real and rationally convex. If I just want to take a surface and I just want to put it inside C2 as a rationally convex subset, I just care about embedding it in some way as a rationally convex subset, then they obtain rationally convex embeddings. And when I say these are sort of singular, so these are only topological embeddings, they are kind of coming from Lagrangian embeddings, but you're allowing certain singularities. And once you allow certain singularities, then this result doesn't step in. So they have rationally convex topological embeddings of all surfaces except for the 2-sphere and RP2. Okay, and we don't know, so this is one of the open questions that I put in the note over there. We don't know if there's a way to embed, I mean, you're allowed as bad an embedding as long as it's just homeomorphic to the image. I mean, it's totally fine. I just want the image to be rationally convex. And I'll sort of tell you why. This would be of interest. So here this is open. Do S2 and RP2 admit rationally convex topological embeddings into C2. And so most smooth examples are not, I mean, this is sort of a delicate problem because earlier, in the morning when I gave you a set of examples, I asked you to think about the standard 2-sphere in C2. And what this was, it was x1 square plus y1 square plus x2 square equal to 1, y2 equal to 0. And the reason I gave you this example was because it's not totally real everywhere. I'm not asking for any differential condition over here, okay? So I'm just asking for topological embeddings. But let's start with a nice 2-sphere. It's not totally real at exactly 2 points. And it turns out that these 2 points are actually quite fatal. Like from the point of view of convexity, they make all the difference. You have a whole bunch of holomorphic disks. And these holomorphic disks, they sort of land in the hull of this set. So let's call this K. They sort of land both in the rational hull and in the polynomially convex hull, okay? But this is just one smooth sphere, but there's a lot of work to show that generically if you take a smooth 2-sphere, you will have points like this and they will have these disks attached to them, and that will create a problem with convexity, okay? So whatever this embedding is, it's probably quite bad if it exists, which is what makes this problem quite challenging. Okay, so since we've come to this discussion of disks, I kind of avoided talking about disks for a while, although that's something that one should do when talking about hulls. So, I mean, where did this sort of discussion, this whole connection to symplectic geometry really start? So it started with this theorem of Gromov, who was studying, I mean, he was interested in symplectic manifolds. He was actually interested in the sort of symplectic structures and almost complex manifolds. And so this theorem I'm going to state, I'll just do it in the setting that matters to us, but there's a more general statement over here. So let M, this is real n dimensional, Cn be a Lagrangian, so be a closed, and by closed I just mean compact without boundary, Lagrangian submanifold of Cn with the standard structure, standard symplectic structure. Then he showed that there is such a disk attached to that manifold, and I'll write what that means. Then there exists an F which is continuous, and it goes from the closed unit disk into Cn. It is holomorphic in the interior of the disk. Okay, so you have M here, this is some Lagrangian submanifold, and you have this disk which is sitting inside C, and remember this is all sitting inside Cn, so we can talk about holomorphic maps from the unit disk to to Cn. And what we also have is that the boundary of the disk sits inside the manifold. Okay, so this is known as an attached holomorphic disk. What you're getting is the image of this sort of looks something like this. I mean, it could have singularities, it could have this is not like some sort of regular embedding or anything. So this is F of D closure. And the boundary of the disk is landing on this Lagrangian submanifold. So what consequence does that have? So what does that immediately tell us about the convexity of M itself? So as soon as you have something like this, you take something which is, you take a polynomial over here, you take a polynomial in a holomorphic polynomial, you pull it back by the maximum principle, its values at any point on this disk are going to be absolute values of those, values is going to be dominated by the values on the boundary, and the boundary is sitting inside M. So let me maybe write this down. So consequence, this entire disk, the image of this entire disk is sitting inside the hull over here, and it's going to give us something extra in the hull. Why is this not all sitting inside? So let me write it this way, yeah. So why is this entire disk not sitting inside M itself? I mean, okay, fine, it's in the hull, but why don't I have this disk actually sitting inside M? I mean, remember that M was a Lagrangian submanifold. In particular, it's totally real. It's not going to contain anything holomorphic inside it, okay? So, excuse me, this necessarily gives us something extra in the hull. We already did know that M has non-trivial hull because it's an n-dimensional closed submanifold of Cn, and I've said already that there is some topological issue with it having polynomial convexity, but this is more. I mean, it's giving us very explicit objects in the hull. So this is a stronger statement. In general, you may have non-trivial hull and you may have nothing like this over here. You may not have these attached disks over here. So whatever technology Gromov used, it was quite useful in producing sort of more explicit elements in the hulls of sets which were not polynomially convex. And they were also useful outside of the setting of Lagrangian submanifolds. Okay, so there is a lot over here. It doesn't fully work. I mean, there are issues when you exit the Lagrangian setting, but you can get some sort of statements. Okay, so so I now want to let me see what else I wanted to say over here. Right. So I want to go back to Duval-Sibony, and I want to mention a few things that came out as consequences of that. So some consequences of, and when I say Duval-Sibony, it's not just the result that I have stated, but as I said, they have many results. They also have results in the setting where they're interested in rational and polynomial convexity of omega closure, where omega is a domain in Cn. So the first one, this is not a consequence, it's known that this condition, it is known that being, and we are always in the smooth category, being smooth, totally real, and polynomially or rationally convex, either of these two convexities is stable under C1 small perturbations. In general, convexity is not a stable condition. This is something which is quite delicate, but if you have all these nice features, you have a smooth submanifold, it's totally real, and it has convexity over here. So this goes back to Fosnerich, and then the C1 part comes from Leff and Wold. So this condition, so once you have this, then this is stable, and that C1 small perturbations are going to maintain being both totally real and whichever convexity you have. So that means your approximation problem will also be preserved. Remember that these two imply very strong approximations, but Nemirovsky used Duval-Sibony to show that this is not true for C alpha perturbations. So these are Holder perturbations. Yeah. So he produced explicit examples. In fact, he produced sort of tori, two tori in C2, which just come as, so they're smooth, but they are just C alpha perturbations of a totally real rationally convex torus. In fact, they are perturbations of the standard torus, but they are C alpha small perturbations. And then he used the fact, he sort of showed that they're not Lagrangian with respect to any scalar form, and therefore was able to conclude that they are not actually rationally convex. So you have to use the fact that there are some invariants that are attached. So if you have a, let's say, totally real torus, you can compute certain invariants to tell whether it appears as a Lagrangian submanifold or not. Okay, so there is a fair amount of work involved over here. And let me also switch to this setting, omega closure, which brings us to the second open problem that I mean, this is a big famous open problem. If you want to think about polynomial convexity, this is probably the kind of problem that, I mean, it's sort of strange that we don't know the answer to this. So this is Carlin's open problem. Is the union of 4 or more disjoint closed balls polynomially convex. Balls in C2, let's say, polynomially convex. So I'll sort of explain the context. I mean, I'll explain what is known, and I'll tell you how it's related to Duval-Sibony. I mean, it's very easy. You can really just define polynomial. You don't need any of the stuff that we discussed in the last 4 lectures. You can really just start with the definition of polynomial convexity. And what we are asking, so we are in C2, and you take closed balls, they're disjoint, is the union. So we did talk about intersections of polynomially convex and rationally convex sets, but we also said that unions are quite delicate. So for 2 balls, if you just take 2 balls, you can try and show this by hand. 3 balls is more complicated, and that is Carlin's, I mean, it's called, Carlin solved that problem using something called Carlin's lemma, which is a very classical tool to establish polynomial convexity. But this problem is not known as soon as you have a 4th ball over here. Is this union, can you somehow arrange these in a way that you lose polynomial convexity? Okay, and there are lots of special cases that are known. So if the centers lie in Rn, this is true. So if they lie in this totally real plane over here, this is true. Not true if you change balls to ellipsoids. There is a counter example, but I think this counter example is in C3. I don't know if there is a counter example in C2. So this is sort of very delicate. This is really a problem for balls, yeah, for disjoint balls. And so what does it have to do with Duval-Sibony? Well, whatever machinery they cooked up, that was, this is again due to Nemirovsky using Duval-Sibony, but not the result I have stated here, something from that same work. The disjoint union of finitely many balls in Cn is always rationally convex. Okay, so as I said, the original problem when this was stated, the result for 3 disjoint balls is very, I mean, it's sort of very hands-on. Carlin's lemma is a very hands-on approach where you use, you sort of cook up the right polynomials and you play around with that and you establish polynomial convexity, but this is a much more abstract approach using these PSH functions and this characterization of Duval and Sibony. Okay, so this is, I mean, once you take something for granted in Duval and Sibony, this is actually not that hard to read. It's a very short paper. But yeah, it's not clear if it gives anything for this open problem over here. Any questions? Okay. Yeah. All right, so last bit of, again, I'll just state some things. So this is due to Eliashberg and Silipak. Again, using sort of techniques more from symplectic geometry. What they were interested in knowing is, can you characterize the topology of omega so that omega closure is either rationally or polynomially convex. I'm only going to state the statement for the rationally convex case. There's additional condition needed for polynomial convexity. So let omega in Cn be a smoothly bounded, so they always work with smooth domains in their setting, smoothly bounded domain in Cn. The important thing over here is, and this is another source of open problems, they actually only have this statement in dimensions 3 and higher. And in fact, in dimensions 2, the situation is quite different. So you have a smoothly bounded domain in Cn, then omega closure right. Omega closure is smoothly isotopic. So it's okay if you don't know what this means, but it just means that you can somehow deform it to a rationally convex and they use this word, this phrase, compact domain. I mean, by compact domain, they just mean closure of a bounded domain. If and only if, and they have a condition which I'm going to write down. It involves Morse functions, but I'll tell you from the SCV point of view what it means. In if and only if omega closure admits a Morse defining function with so what was the exact condition? Was it greater than, let me see, greater than, Yes, critical points of index with no critical points of index greater than n. So it's okay if you don't know what all these words mean, but from the point of view of several complex variables, if you've heard this word pseudo-convexity now enough number of times, this condition is exactly the condition, it's sort of a necessary condition for omega closure to be the closure of a strongly of a pseudo-convex domain. Okay, this is exactly the topological condition, and they're sort of saying that topologically there is no difference. If you can find a pseudo-convex embedding, then you can isotope it and make it rationally convex. Okay, that's what this statement is saying. There is really no, at sort of the topological data level, there is no difference. If you want polynomial convexity, you have to add something over here, which I'll not go into. But that's what this is saying. So there is a whole body of work which sort of tries to understand. I mean, of course, in dimension 2, there are some special cases that have been studied. So there is work of Nemirovsky and Siegel, and there's some very, very recent work by two contact geometers. I mean, they don't have any background in several complex variables, where they study very simple three-dimensional real manifolds. So they study these things called homology spheres, and they want to know when can these spheres appear as smooth boundaries of rationally convex domains like this in C2, or when can they appear as smooth boundaries of strongly pseudo-convex domains in C2. And so, I mean, that itself, I mean, if you take the topology to be very simple of this three manifold, so they are sort of starting with the object that's going to act as B omega. And that's the object they want to start with, and they want to understand when can you embed it diffeomorphically into C2 so that it bounds something with the right convexity property. So this doesn't work, whatever this is, it's just not true in n equal to 2, and there are examples by Nemirovsky and Siegel where they, in their paper, they study a class of disk bundles over surfaces. So they want to work in C2. You take a surface that's real two-dimensional, you take a disk bundle over that. That doesn't quite work. Yeah, it does work. So you take a disk bundle over that, you get a real four-dimensional domain, and so they try to understand which of them can be isotoped to a rationally convex compact domain. Okay, and I think, yeah, I'll stop over here. Thanks.